It's our great pleasure to welcome Professor Eli Yablonovitch from Berkeley here to give a talk. He's an IAS visiting professor, so he visits us regularly. And Eli just won a very prestigious award, so-called the Isaac Newton Medal and Award from UK's Institute of Physics for his seminal work in the photonic nanostructure, right? And Eli have won many other awards, but this one is really for, as we all know, Isaac Newton cover wide areas in physics and math, and including optics. And so clearly, Eli is in the highest echelon of living scientists and scholars. Eli was also a member of National Academy of Science, Engineering, and Royal Society and AAS. So we're very happy that Eli is going to give a talk which is very provocative, interesting. We will find out. Okay, so let's welcome Eli.
You can see me, I can see you. That's fine. And is the audio fine? Audio's okay. Okay, so it's kind of a scary title, and it is a little bit controversial. I have given this talk twice already, and I've also taught it this last spring in a course. So it should be interesting. And you'll see what my motivation is in just a minute. But first, let me start with national motivation. This is actually my other laptop. Oh, I wish I could write on this. I have to use this now. Oh, and I see it doesn't help if I change the slides on here. I've got to change the slides here. Okay, so here we have the other laptop, which is in the guest house, okay, which probably would not have had this difficulty with the video resolution. Usually, it's better to be backward compatible. This one is forward compatible, but unfortunately, I only took one laptop lecture. But on the subject of laptops, it's kind of interesting. And the subject is how the clock speed used to change. Now, many of you are students, and you're too young to remember when the biggest selling point of a laptop was the clock speed. Okay? And let me do a quick survey of the students. In 2002, clock speed saturated at about 3 gigahertz. It used to be a big selling point up until 2002. And after 2002, the clock speed is more or less constant. Now, who can you raise your hand if you're old enough that you bought a clock speed based upon a faster clock speed, a computer based on a faster clock speed? So only a few of you, and so the younger students didn't do that. So it's been approximately constant. I have to wonder why that is. Now, it turns out I'm the leader of a center in the United States, and our center has been given a task by the National Science Foundation to find a replacement of the transistor. So we need to understand what we're trying to improve. And immediately, there's a problem. The clock speed has not improved. Is it possible to increase it? Now, is it a constant? Yes, it is a constant since 2002. Is it a constant of nature? That's unclear. Okay, has it reached a plateau because of fundamental limitations that we can't make any improvement on? So this is a rather serious question, especially for the most important technology of our time. Let's go to the next step. Actually, this one, my new one, is in the guest house, is only 2.2 gigahertz. So, by the way, the battery on this is flashing. Find a replacement. Okay, so can we go faster and faster? Can we go faster and faster? We always want to go faster and faster. For example, we could ask the question, if you want to measure one electric charge, how how fast can you do it? It seems fundamental. It's one electric charge, so there's a fundamental limit associated with that. Now, there are two possible answers which are at odds with one another. And one answer is that if you try harder, if you put in more energy to do the measurement, if you spend more money, get a more expensive instrument, you will get a greater speed. And the other viewpoint is we're up against a fundamental speed limit. Now, if it's fundamental, then it has to be connected to fundamental things like the constants of nature. So everybody's clear on it. By the way, I invite questions. Kind of an accessible topic even to undergraduates. So if it's fundamental, we have some constants that we're accustomed to. We have these fundamental constants, all these numbers that you've seen. And however, there's a particular combination of these numbers that is very interesting. So this is a very famous combination. I'm worried that this H should maybe, H bar maybe should be an H. So we have this particular combination, and it's very famous in physics. It's called the fine structure constant. When I was a student, this was a very mysterious number, and it was thought to be important in atomic physics. Now, this has changed. Now people recognize this is a universal number. We'll see on the next slide what the number represents. So what about this combination? Well, it uses many of these. It does not use the mass, but it uses the other fundamental. What can we do with the other fundamental constants? Well, the speed of light today, this is actually not a measured number. This is now a defined number. So about 30 years ago, they decided stop measuring the speed of light. Let's define the speed of light. It's just a connection between similar units. 1 second is fundamental. And the distance, instead of being centimeters, is just the distance that light can go in 1 second. And so they defined this to be the constant that connects it to. It's a defined number. After the 8, it's all zeros. Now, of course, they could have done differently, like in high energy physics, they just say the speed of light is 1. They could have just chosen it to be 1, rather than official choice today, but you could have chosen it to be 1. Similarly, for the Planck's constant, you could measure energy in joules, or you can measure energy in frequency. It's just your choice. And if you decide that it's the same thing, you can just define h bar equal to 1. Okay. And you can also say, oh, 4 pi epsilon naught. That doesn't even appear if you use CGS units. It doesn't appear. And so you can make the 4 pi epsilon naught equal to 1. You can just make a different choice of units, like in CGS units. So the result of all this is that there's a great simplification. When you simplify all this, everything disappears. And this constant, fine structure constant, fine structure relates to atomic spectra. But you see, if you choose the right units, it's just the electric charge squared. It's actually 1 over 130. Actually, I think the 4 pi should. So we've taken the 4 units. We got rid of 2 of them. We defined the speed of light. We defined the Planck's constant. We only have 2 left. One of them has no dimensions. It's 1 over 137. It represents electric charge squared. So that means electric charge squared is the square root of 137. Is 1/11th, is a small number compared to 1, and because it's a small number compared to 1, we can solve problems in electricity and magnetism. We can solve them quantum perturbation method. That is very important. And we have only one other constant, the rest energy of the electron. Now, according to my claim, if I go back, these are all the constants that are needed to biology, chemistry, electrical engineering. Those are all the constants I need. And now I'm down to, I got rid of 2 of them, so I'm down to 2 constants. I claim that with these 2 numbers, I can define all of chemistry, biology, and this is the first of my extravagant claims. But you'll see at the end, you decide at the end of the talk, is that really true? Now, what can I create that has dimensions? So the only thing I have that has dimensions, energy. Energy is the same as frequency, Planck's constant. And so it seems like there's only one energy, but there's actually a whole series of energies, because I can multiply 511 kiloelectron volts, I can multiply it by the dimensionless number. Other energy you never heard of, but it's related to the Compton wavelength. So it's the Coulomb energy between electron and a proton separated by the Compton wavelength. We don't use that very often. What if I take the square of the fine structure constant, multiply it by the rest energy, take the square, and now I do some manipulations, find these things. I have this q squared over 4 pi epsilon naught, that's just a charge. But this thing, maybe you recognize it, maybe you don't recognize it, but it's actually 1 over the Bohr radius, which is kind of remarkable all by itself. And this is the Coulomb, actually the binding energy of the hydrogen atom. It's 2 times the binding energy of the hydrogen atom. So the hydrogen atom has a binding energy of 13.6 eV multiplied by 2. So now we have access to all the energies of chemistry. Because energies of chemistry has to do with the binding of electrons. So it's 2 times the hydrogen binding energy, and it's actually around 3 times hertz units. Okay, so I think I have a pretty strong case, at least for chemistry, that I've entered the realm of chemistry. That this, divide this by 2, I get my 13.6 eV. And all of the binding energies in chemistry are related to the 13.6. Just to add another dimensionless atomic number for generate all of chemistry. Generate all of chemistry, you generate all of biology. Electrical engineering, I will get to in a couple. Okay, so does anyone object? You can object now, or you can object later. But so far, I claim there's only one number in chemistry, biology, and electrical engineering. It's only one number with dimensions, has dimensions of seconds. So by the way, I am very fond of dimensional analysis. Part of the reason that I am doing this is that I have been I always think about dimensional analysis, always thought about it. I was very surprised that I could get the clock speed of a computer from dimensional analysis. What this says, any experiment I do that has units of time, in physics, they're kind of physics that we do. Only one thing that has units of time, so everything has to be connected to this plus the dimensionless number. So let me just ask a quick question. How many of you were aware that if you took the rest energy of the electron and multiplied it by the fine structure constant squared, that you would get the binding energy of the hydrogen atom? Anyone aware of this? Yes. Obviously, the professors are masters of this, and obviously the theoretical physicists do this all the time because they always take H bar. Okay, so let's move on. So what can we do with computers? What can we possibly do with computers? So we try to do many things. Try to have the computer use as little energy as possible. Now, my new computer, which I left in the guest house, actually just as fast as my old computer, which is 5 years old, which is that I try to use. And they're both equally fast. They're both stuck around the same speed, but my new computer, the battery lasts 12 hours. We're always trying to reduce the energy. So we could ask, how small an energy could we possibly use? So this was already expressed by a famous theoretical physicist from IBM. He said it has to do with thermodynamics. The least energy is energy reset a bit. It has 2 states, so entropy is log 2 multiplied by thermal energy kT. He says this is the theoretical limit. This is the least amount of energy to form one computer function. However, if you try to go too fast, you reach a limit. But you can go a little bit faster, but it's going to cost you a lot more energy. So this resolves the issue. There is a bit of an issue, especially in my field, having to do with transistors. They say, well, is it the power delay product? They're always talking, Intel, all those big companies, what's your power delay product? The energy per digital function. Okay, and that tends to be a constant. And then if you try to go too fast, it's not the uncertainty principle, but if you use more energy, you can go faster. But it's a point of diminishing return. So this is roughly where we are, computers today. Now, but in reality, we're not quite here. In reality, we're a little bit different. And let me tell you what is wrong with computers. This is a slide I use to explain why we have an NSF center, a national center. So I have 5 universities, 19 professors. We're all trying to replace the transistor. And what's the problem with the transistor? Well, the problem is if you figure out the noise in wires, well, the noise is usually microvolts. Anybody who's ever used an oscilloscope, you go down below a millivolt and suddenly it gets noisy. And so if it's just noise in wires, say, well, you'd run it at a low voltage and the wire would be happy with 1,000 electrons at 1 millivolt. However, the transistors are following the Boltzmann factor. By the way, we have to defeat the Boltzmann factor. You'll see why in a second. And because we're limited by the Boltzmann factor, we say, well, what's the energy? What's kT? If you measure kT in volts, you have to divide by charge, and it turns it into volts. kT is 25 millivolts. Very common, commonly understood. But you have to be careful. It's volts, it's not electron volts. Now, to turn a transistor off, you cannot just turn it off with 25 millivolts, because in a computer, we have to have a good on-off ratio. We have to be able, when we turn it off, in a computer, most of the time, it's waiting for data. The transistor is just waiting for something to happen. So when we turn it off, we want it to stay off. So we need an on-off ratio of 1,000,000 to 1. Well, how am I going to get a Boltzmann factor with a probability of 1/1,000,000th? To do that, it's not, kT is not enough. You need the 12 kT, that order. And 12 kT is 0.3 of a volt. So, and in practice, you end up needing about a volt, close to a volt. So our transistors are operating today, most up-to-date computer, maybe 0.8 of a volt, but the wires are happy at 1 millivolt. So there's a big disconnect. The wires would be happy at 1 millivolt, the transistors need 1 volt. We're off by 6 orders of magnitude because voltage has to be squared to get power. So everything in electronics is 1,000,000 times less efficient than it should be. And so that's the problem that my NSF center is trying to solve. We want a transistor or device much more sensitive than today's transistor. We want to operate closer to a millivolt. Signal-to-noise ratio says we should be able to operate closer to a millivolt. So this gets us into this situation. In reality, we are 1,000,000 times worse than thermodynamic limit that Rolf Landauer up with. We're stuck up here, but it's okay. The speed is roughly, gets bad at roughly the same point, 3 gigahertz. So we're compatible with the people who believe it's more like energy times time. They're correct also, and people who believe power times time, they're correct in this region. So this is today's computers. My center's goal is to lower this. At a pen, I would write little downward arrows here. But this is roughly where the industry gets stuck. They rarely turn this corner. They hate to spend extra. What is our goal? Center is, this is true for every transistor, operates on a simple principle. We have a barrier. Electrons have to jump over the barrier. They're controlled by the Boltzmann constant. Because of the Boltzmann constant, we want to get to low probability, so then we have to have e to the minus 12 probability. This is true for every transistor you heard of, carbon nanotube transistor, just all different types of transistors. They're all controlled by the Boltzmann factor. So one of the problems I had when I wrote the proposal How can you possibly defeat the Boltzmann factor? That was one of the questions that the referees asked. The way we defeat the Boltzmann factor, we find a different mechanism. Instead of taking 0.3 of a volt to turn on and off, we simply want something that has a more sensitive switch that is off. So just that convincing, so they gave us a very big national research. Go look for a switch. So that would deal with how to lower this part of the curve. What about making it faster, though? Faster. There's a question. Here, we'd like to go faster. What's the limitation? So here are the requirements for the new switch. So we have been living and breathing for the past 5 years. What is the replacement for the transistor? What properties does it have to have? So it has to be more sensitive. So electrical engineers, they have a different way of describing the Boltzmann factor. Instead of a factor E, they do a factor 10. So 25 millivolts for a factor E is 60 millivolts for a factor 10. So they're always trying to beat the Boltzmann factor. So they say, what do you have? They publish a paper, 59 millivolts. Okay. That's already to get a paper, good enough to get a paper accepted. Imagine what that's like. And then they publish 53. Very, very tough to make progress. In fact, they have not made any progress. But we don't want 53 millivolts per decade. We want much more sensitive, maybe 1 millivolt per decade. And we need the on-off ratio I talked about, because most of the time. Then we need something that is the subject of this talk, is how much conductivity does one transistor have? Depends on the size. And today, if you ask an engineer, he'll say, I need to deliver a milliamp in a 1 micron size device. However, if we reduce the voltage, the milliamp becomes a milliamp. So you have to deliver a conductance of a milliamp. Siemens is reciprocal ohms. A 1 micron device should conduct at 1 kilo ohm. This is the borderline, that's sort of the threshold. Then maybe it's good enough. So that is kind of interesting. This will turn out to be exactly what limits the clock speed of your ability to deliver conductance. See, it doesn't have much to do with that has sort of been recognized. You're stuck with a 3 gigahertz laptop, and the transistors are able to go much, much faster. And so it's not limited by transistor speed. That you should find. Okay, now I get into something a little messy. I wish I could write on this screen. This is a slide I use in my class. I'm trying to derive that if you had the perfect wire, that it won't have infinite conductivity. It will not be a superconductor. Even the perfect wire will not be a superconductor. Perfect wire will have a certain amount of resistance. And that resistance, imagine here a perfect wire with a little barrier in between. And we're going to take the barrier away. Have the Fermi sea of electrons here, and there's a lower Fermi energy. The difference in Fermi energy between here and here. That's your applied voltage. I'm not going to go through the steps, but the final result is a very famous result. But I have to check with a show of hands. I've heard of this before. Is that if you have the perfect wire, this would be the resistance. Q squared over H, another fundamental constant. That amount represents 1 over 26. The perfect wire has a resistance of 26 kilo. Try to aim higher conductivity, you need 2 wires, sort of quantized. Now, maybe you find that to be very strange. How can 26 kilo ohms be quantized? Because you can go get a resistor of 27 kilo ohms. You can get another one of 25 kilo ohms. So a little bit strange quantization, but it represents a perfect wire. So there it is, the quantum of resistance, and roughly 26 kilo ohms. So that's kind of interesting. I need to have a show of hands. Anyone, graduate students, undergraduates, who is aware that the perfect wire is only able to deliver conductance corresponding to 26 kilo ohms? That's something new? I tried this also in other countries. Apparently, this is not taught that often, but among the people who work in nanoelectronics, they all know this. Perfect wire. I'll show you now, next slide, I'll show you an experiment to how it's been validated now. Of course, it's been validated many, many different ways. But let's do one more bit of dimensional analysis. I told you whatever you have, you're allowed to multiply it by a dimensional. So this has dimensions, it has ohms. Let me multiply it by the fine structure constant. If I do that, cancellation, you see, if I was writing, I could cancel. So forth. I end up with this combination of epsilon naught times t. Notice I'm religious about MKS units. This relation gets square root of mu naught over epsilon naught, which is 1/2 of another famous number. This particular number is not acknowledged by theoretical physicists. With all due respect to the theoretical physicists, if you use your normal units, this will end up being 1 over the speed of light. It's not going to look like anything special, but I'm actually an engineer, so I insist upon using units. I end up with the impedance of free space. Now, this should set off alarm bells immediately, because you have two resistances, both of them fundamental. You have 26 kiloohms, that's fundamental. And now we have the impedance of free space, 377 ohms, that's fundamental. But now we're sort of accustomed, yes, of course, because we're allowed to introduce a dimensionless number. So the dimensionless number we introduce is fine structure constant divided by 2. I have this up. But it's basically 137 divided by 2. Okay, so that's kind of interesting that there are two impedances. This is an important thing to learn. Now, it used to be that the only people who knew about this 26 kiloohms were low temperature physicists. And this is a quantum mechanical property, this conductance, it has H bar in it. And so they said, well, I'm a pure physicist, and I do fundamental experiments. I have to go down to 1 degree Kelvin. But later it was realized that this particular property has nothing to do with how cold you are. You just need to have a very skinny wire. Imagine that you have 2 gold wires that are touching, and then you vibrate them, and as you vibrate them, they pull apart. There's a little last part to break, 2 gold wires. That little last part to break is like a very, very skinny wire. And this can be done at room temperature. They vibrate the 2 wires together, and they measure the resistance to the wires. There it is. It comes out as the conductance quantum. This is now an undergraduate experiment. Henry, you're from Cornell. Your students get this, okay, at Cornell. They are, some of them are expected to take it. And it is rather remarkable that you end up getting conductance quantum. So it is not so mysterious. Have the conductance quantum is the fundamental resistance. So I dwell on the conductance quantum for the following reason. It's going to turn out the clock speed of your computer depends upon the ability of transistors to deliver conductance, and at best they will deliver a certain number of conductance quanta, very best. This is going to limit the RC time of the wires in your microprocessor. That RC time limit is going to be the real limit of the clock speed of the computer. It has nothing to do with the transistor speed. Faster. That's my program. I have a little bit of time to do this. Now, what's the most important thing? Wires. Okay? This is showing you a cross-section of a computer. You see wires and a little bit of a cartoon there. This is, we'll get back to the wires in a minute, but I have to say something about wires. Maybe you heard that a computer relies upon logic. And logic is a great, wonderful thing, but actually it turns out logic is relatively easy to do. It can be very efficient. This is very close to the fundamental limit. Similar to the Landauer limit, but allows for some good signal. And you say, well, my computer needs storage. Memory, storage, and flash drive and so forth. Well, those flash drives, they can also be quite. And you say, well, my computer also needs communications because the transistors have to talk to one another. And that turns out to be the hard part. Very hard to communicate. And in fact, this is an underestimate. We're not even there at 100,000. We're more like 1 million KT. And we've been stuck here for a very long time, maybe. We've been stuck with the voltage. The voltage has stopped improving. Because of the voltage, signals on wires, 1 volt, stuck at 1 million times less efficient. So the communications is actually very important. And here's the main type of communication. This is the new Broadwell technology. So if you buy a brand new computer, you will get this chip. There's a company in Silicon Valley that first engineers the brand new chips. Shows people for free. You can download this from the web. It shows people what the wiring looks like. So here are the wires that are used in the chip. You have big wires. As you get closer to the transistors, these tiny things here are the transistors. You can hardly see them. And stacked up here, you have 4 wires which you cannot quite resolve those wires. 4 more, and so forth. You end up with about 14 or 15. This is actually the 12th one. There's actually 2 above here that you cannot see. 13th one. This is in your newest computer. So I ask you the following question. What is more important, the wires or the transistors? Well, say we have 14 layers of wires, but we only have 1 layer of transistors. So it seems to me the wires are important because you don't have very many options. Communication is the hardest thing. It has to go at the speed of light. So I was discussing yesterday at dinner that computers are relativistic because signals on the wires are going at the speed of light. One way to think. But it shows you one of the limitations. This is totally amazing, but it tells you what the real problem is. So in my center, we're adopting the following philosophy. We said we will replace the transistor, but we don't see any replacement. Our view, the wires are more important. They're unreplaceable. And this gives you an idea of the size, what you were just looking at. This is a website. Of course, it tells you now, they're cheating a little bit. They call it the 14 nanometer node, but the half pitch is 52 nanometers. So it should really be the 26 nanometer node. So they cheat a little bit. Maybe here you divide by 2, it's the 20. They cheat a little bit. But this is very important to us. It tells us the spacing of the wires, the interconnect. Wires are interconnected. So this is in new computer, smaller than your older. So you can learn a lot of things from analyzing the wires. So I say, let's analyze the wires. It's very important. So for example, you can, let's say you have a wire, it's a rectangle, has a certain resistance. Formula that every undergraduate learns is resistivity times the length divided by the cross-sectional area. Capacitance is proportional to length. Something that everybody should know. Capacitance is, but fortunately, you don't teach that. How to estimate capacitance. You take the length. I asked the students, what's your personal capacitance? I didn't know I had a personal. Well, they're 2 meters tall. They can figure out their capacitance because, oh, this is the same thing. You have a wire. Capacitance. Now, I do the RC time. The RC time, I end up with a dimensionless ratio, the length of the wire divided by the width of the wire. And if I insist a certain RC time so that I can tell the computer I need to have a decent clock speed of 10 gigahertz, a little better. So it ends up, finally, that the wires have a given aspect. This comes up over and over again. Get dimensionless ratios. Amazingly, this one, it's not a constant of nature, but these are constants we don't have much control over. The resistivity, we're already using the best metal. Dielectric constant. So this is an interesting fact. Fortunately, the wires on the transistor are permitted to have an aspect ratio of 5,000, means very long compared to their width. And the way you send signals to the chip, if you have to go a long distance, you go length, 4,000 or 5,000 times the width, then you re-amplify, and then again and again. And so on chip, you might have to do this 10, 20 times before you just, the other question is, how do I know the capacitance of a wire is just proportional to the length? So you can figure this out from coaxial cable. Here I would draw, as you have a coaxial cable, and look up the capacitance of a coaxial cable. I just jumped to this one. Capacitance per unit length depends upon only logarithmically. Famous Coulomb logarithm depends only logarithmically on inner to the outer diameter of the coax. Logarithm doesn't depend on geometry, so it's always around 7, so it's 2 pi over 7 is roughly 1. Capacitance per unit length is proportional to length. These are ways of making good estimates. Now we come to what is the clock speed of my? So I say there's an issue. The purpose of the transistors, in my view, is not logic. The transistor's main objective is to send signals along wires. And some of the wires are long, some of the wires are short. Now, you have a long wire, a lot of capacitance. So you have to have ability to deliver conductance longer wires. The way engineers do it is, if you have a long wire, you need to make a wider transistor. So in the language of transistors, the short dimension called length, big dimension is called width. I'm sorry, that's how they do it. So this they're trying to make shorter and shorter because the transistors, the electrons have to jump from the source to the drain, so they want them to be very close. So the length is very small, but if they need a lot of conductance, they just make the transistor very wide. So there's a fundamental issue here, is that if I have a long wire, I need a wide transistor to drive it. Well, let's figure out how wide my transistor has to be in order to drive a long wire. And some of the wires are rather long. But it's going to be a dimensionless ratio, because load, you have to have a resistance, C time. So let's talk about the relative area. This is just geometry, no RC times. Remember I showed you, let's see, yes, I showed you this slide. There are a lot more wires than there are transistors. Transistors are down here at the bottom. Very few transistors, a lot of wires to deal with. And so you can't simply make the transistors wider and wider because you don't have room for transistors. There's 14, example I gave, there was 14 times more wires than transistors. So the wires, yeah, there are a lot of wires. So there are 14 layers of wires, but you have to drive it with one layer of transistors. So you have a fundamental rule that the transistors should be 14 times smaller wires, because you run out of room. So well, let's see what implication this has for the relative size. So rule for capacitance, I have an RC time. Now, I want to look at the RC time. It depends upon the capacitance denominator. I have the conductance in the numerator. I'm calling K conductance per width. Usual engineering rule of thumb is kiloohm per micron, so it's 10 minus 3 Siemens micron. I pull out the W over L, the width over L. We're trying to find that. Width over this L. How wide my transistors are permitted to be before I run out of room. Put in here these are currently what's required. Plug in parameters, and what you find here, well, you get a certain RC time. Well, how wide can I make device? Just make it arbitrarily wide, and maybe 1/14 could be kind of some number, but plug that in and up it leads. Transistors have to be way smaller than the wires. Finally, you end up with a clock speed. Today we have a clock speed of kilohertz, which is roughly today's clock speeds. But I didn't use any fundamental constant. Put in engineering parameters. Now, let me describe a real transistor. A real transistor consists of a panel, and then the electrons are going this way. But they're wave functions. You can only crowd a certain number of electron wave functions width of a transistor. And the wavelength is determined by the thermal energy. And so it's like you have channels. Each channel has a conductance of 26 kiloohms, but you can't crowd them very closely together because this ends up being about 10 nanometers. Not that closely spaced wavelength. This is, can't crowd them together very much. So this is why we're limited to kiloohm. How can we improve it? Well, we can improve that by making carbon nanotube transistor. Now, the carbon nanotube transistor is better, but not because it's faster. In fact, it has nothing to do with how fast the transistor is. Carbon nanotube transistors, they have conducting channels. They can space them much more closely. So get more conductance. That's the key. More conductivity is more important than more. So we can crowd the carbon nanotubes together. Each one would be one conducting channel. And we say, well, how closely can we crowd the carbon nanotubes together? Well, it's related to the Bohr radius, right? Because little structure, molecular structure, all connected to the Bohr radius. Some number, this periodicity, pack them as close as you can, but it'll be some number times the Bohr radius. That's how close you can pack them. 20 times the Bohr radius, and you're packing them 20 angstroms apart. In practice, you can't do that. You can't quite pack them that close. We'll try to pack them. So what I'm going to do is very simple now. I'm going to figure out the conductance you get in this ideal transistor. I'll get an RC time. I'll pack them in as closely as I can. I'll get the maximum conductivity possible per unit width. So I had previously a kiloohm per micron, and now it's going to be conductance quantum per periodicity, which is related to Planck's. No, I'm going to end up with fundamental constants because it's related to Planck's or radius. So here I do the same thing again as I did before. I have the conductance quantum, have the conductivity, so conductance quantum times the conductance per unit width, so the width is W and the number of channels 1 over the spacing of the channels. Spacing of the channel is radius. I have the capacitance wire. Follow through, I collect terms, up or radius in the ratio here was the amount of crowding I could take the Bohr radius, we plug in the Bohr radius, and now you see the clock speed of my computer is going to be related to Bohr radius. It's going to be related to the Bohr radius through the Rydberg binding energy. Now I have my clock speed of my computer, and now I have some dimensionless factor. Number of Bohr radii, spacing, carbon nanotubes, crowding, how much crowding, how big my transistors have in relation to the length of the layers. 14 layers of wires you have to draw. And finally, I collect everything. It's all fundamental constant, the Rydberg energy that I started. 13.6 electron volts sounds like a high frequency, 3 times 10 to the 15. But then I divide by electric constant, silicon, 12. Divide by how tightly I can crowd my carbon nanotubes and crowd them back tightly. And I have the dimensionless ratio. The transistors had better be smaller than the wires because the transistors take up too much room. So I multiply everything out, and I end up with a clock speed of 120 gigahertz. So that sounds like it's better. Of course it's better. It's a carbon nanotube transistor. We don't have it yet. But it's not as good as you think. You have to bring in something computer science. The computer scientists, they're very greedy, and they don't care about the device people. Very greedy, and in one clock cycle, they want to complete multiple operations. For example, they want to have a complete add operation. They want it to be over during one clock cycle. So if this is one clock cycle, there to there, that's one clock cycle. They want to go much faster than a clock cycle. So the transistors and the RC times have to be a lot faster. Now, if you then go to computer scientists and say, I know you're greedy, but how many operations do you want within one clock cycle? They say, I'm greedy. I want 20 gate operations in one clock cycle. That's called the logic depth. And so I would say maybe they're greedy. Maybe they'll settle for a logic depth. They settle for a logic depth of 10. And if it's 40 gigahertz RC time, then you get 4 gigahertz clock speed. We had 120 gigahertz. So now maybe with carbon nanotube transistors, we get 12 gigahertz clock speed. So there is room for improvement. But it requires transistors with more conductivity. And so finally, put in all the numbers. I put, let's say, 50 conductance channels, logic depth of 10. 10 divides out. So instead of 120 gigahertz, I'm now down to maybe 12 gigahertz. 12 gigahertz, what you can realistically hope to develop carbon nanotube. It's all of these dimensionless ratios. You're starting with a fundamental frequency, Rydberg frequency. But you have all these dimensionless ratios that are working against you. The fact that you have many metal levels, limited wires are narrower than the transistors are long, and you have other dimensionless number, electric constant, and then you have the logic depth. All of these knock down the speed which you can go, but you're starting with something, I claim, Rydberg frequency, binding energy of fission atoms. So I've more or less reached my conclusion that the clock speed of your computer is limited by the fundamental constants. I showed you at the beginning the Rydberg frequency related to the rest mass of the electron. So I was kind of stunned by this. I've been teaching this for a while, but I didn't realize I could break it down into. I'm expecting some opposition here in the audience. Now, I have 2 more slides. Just to what can we hope for? The objective is to get more and more conducting channels. So now they have FinFET, where they try to get more space for the conducting channels. It helps a little. But if we crowd more and more FinFETs together, normally the FinFET is going this way. I say you get more conductivity if you go vertically. So if you change the FinFET's direction of current flow, you'll get much more current flow because there's more width here. You can crowd these together. So you can actually do better with a FinFET. But ultimately, you would go to carbon nanotubes, but it would have to be vertical like this. This is the so-called nanowire transistor. This gives you more conductance because you have more vertical channels. Wrap a gate all around. Because of the gate, you can't crowd them that closely together, but you do the best you can. This will be the ultimate evolution of this idea that we're limited by RC time. We just need the most conductance possible. This will give you the most conductance. How many vertical nanowires can you use? That's going to determine clock speed, but it's not going to be that much faster than today. Even with the carbon nanotubes lying flat, we only get to 12. So that's what we can hope for. Thank you very much for your attention, and request a lot of questions. I want to see some resistance. Don't accept this right away. Thank you.
So way back, I remember there was another limit for the speed. You hear you talking about the gate, right? The switching time or something like
Well,
that.
no, I started with the switching time. That's the normal limit. But then I said the transistors are much faster than 3 gigahertz. They're way faster. And so it was the RC time. Yeah, go ahead.
There's some computer scientists will
Yes.
say it's just the speed of light. It takes for a signal to go from one place on the computer to another. And that's the
Yeah.
fundamental limit there as well.
Yes, that's right. That's also a fundamental limit. What that says is that across the chip, we have to be able to, within one clock period, we have to be able to jump all the way across. Now, one gate to another is too easy because you're going at the speed of light. So this is critical to the point I made at the beginning. I said, forget about logic, forget about storage. It's all about the wires. We have a severe constraint. You know, we have 20 different technologies for storage. We have magnetic storage, electrochemical storage, mechanical. We have so many ways of doing storage. Logic, we also have a great many ways. But because of exactly what you're mentioning, that we have to go at the speed of light, we only have 2 ways of going at the speed of light, which is wires or optical waveguides. Those are the only 2 ways to go at the speed of light. And so it ends up that you're forced to use the wires. You don't have very many options, except maybe you could go optical. So unlike storage, where you have 20 options, in communication you only have 2 options. So then we're forced to say the most important thing is the wires are more important than the wires have to go at the speed of light. The computer scientists demand it. They can't do it, live without it. But if you are driving wires, you have to fulfill the condition for RC time. Fulfill the condition for RC time, then I say, I need to provide a lot of conductivity. Forget about the speed of the transistor. I have to provide conductivity in order to drive the capacitance. So from the ability to get conductivity, I found, you have the best case is the conductance quantum. You never get more conductivity than that. And oops, it already limits me. And that was the logic. That was to go exactly the starting point. We have to go at the speed of light. And then, therefore, we have to use wires. And therefore, our transistors have to be able to drive the wires. And we have 14 layers of wires. We have only 1 layer of transistors. And with a dimensionless ratio. And they have a whole series of dimensionless ratios. We start with the binding energy of the hydrogen atom, which is 3 times 10 to 15 hertz, which is a phenomenal frequency. Yet with all these dimensional numbers, because remember, we started with dimensional analysis. We only have one thing that has dimensions of seconds. That's the binding energy of the hydrogen atom. All we could do then is introduce dimensionless ratios, some of them forced by the computer scientists. They say, I want to have a logic depth of 10 or 20. I want to do 10 or 20 operations in every clock cycle. Okay, I'm your servant. I will give you that. And so there's a whole bunch of dimensionless numbers. I have 14 levels of metal. That's a dimensionless number. I only have 1 level of transistors. Limited. You don't have enough room to drive all those wires. So that gives you a limitation, your ability to provide conductivity. But that's just a perfect. Yes, go ahead, please.
What determines the transistor width and the length of the wire ratio?
Okay, that ratio, I could go back to that. It's a little bit technical, but talk about it here. But you look at the relative areas. Relative areas. So there's a relative area here. So the area of the transistor is this times that. The area of the wire is that times that. I have a missing slide. Transistors, the wires are the narrowest thing on the chip. Because we're trying to crowd as many wires in as possible. Why? The computer scientists want a lot of communication. So we put as many wires in, as many wires as we put in, they come back and, can you give us more wires? And we're limited because you can't get manufacture after you have a yield. Let's say you have 99% yield on each layer of wires. And now to the 14th power. Suddenly, so we can't have an arbitrary number of wires. So let's say 14, like I showed. And so this area has to be 1/14 of that area. But the transistor, this length of the transistor, to look at the dimensions, you can't. This overall length is more than the minimum length. This A is sort of the minimum rock bottom length you can have, and the transistor has to be a little bit longer. Internal to the transistor is the distance between source and drain. That should correspond roughly to the smallest dimension pattern on the chip. But if you need room for the source, you need room for the drain. So before you're done, this is 10 times higher than that. And now it gives you less room for the transistors have to be bigger. It gives you less room for transistors. And so if I take 1/14 and divide, and then also say 1/10, because this is 10 times longer than your minimum dimension, you end up 1/14, couple of dimensional. End up with roughly 0.006. So that's another dimensional space. 5 at the clock. But very good question. Yeah.
Well, it's well known that RC time delay limits the computer speed. That's why copper metallization is such a big deal. But now, with all the improvements in transistor speed recently,
Yes.
it's not stable. It's still getting smaller and smaller, getting faster and faster. But
Well,
still, the clock speed is the same. Why?
Well, that was my main point of giving this talk.
So
The transistors are getting faster. The transistors now, they're closer to 50 gigahertz. And the clock speed is down at 3 gigahertz. And so the truth is we can keep making the transistors faster and faster, but the clock speed is determined by the wires, by the RC time. And that is sort of...
So the bottleneck is the wiring.
The bottleneck is the wiring. Of course, people went to copper, but copper is like the second best electrical conductor. You can't help the resistance. Very close to the best. We used to have aluminum, so now copper is better than aluminum. So we've already done that. We have tried to reduce dielectric constants surrounding the wires. And what they did is they tried to use materials similar to silicon dioxide, but with a lot of voids. And the dielectric constant would be smaller. It's not a big improvement, but it didn't really work out that well in manufacturing, because in manufacturing, the voids tended to fill up with dirt. So there's very little leverage. Dielectric constant of silicon dioxide, maybe they'll get it down to. There's very little leverage on that. So we're stuck with an RC time. We're doing the best we can. Clock speed can be improved because the resistance limitation was not from the copper. The resistance limitation was their ability to drive. So it could be either one. It could be RC limited by the wires, and I showed you that gave you a aspect ratio of 5,000 wires, which was good. But in the end, more severe limitation from the they cannot deliver the connectivity that we want.
Incidentally, we did a similar analysis for the case of displays, where the mobility of the TFT and the RC time delay of the wiring are both important in determining the ultimate resolution.
Yes, yeah. So that's a great example. If you didn't hear Hoising, he points out to the same issue arises in display technology, where they have the resistance of the wires, so your screen has all these wires in it, and you also have to drive the wires. So you need both the conductance and you need to have your wires having good enough conductivity. By the way, there's a bonus for the students' questions. Because so far, the questions come from professors. Some of them are very smart. They're cosmologists. Now I know I'm in trouble. If the only people who understood my talk were the professors, now I've been talking fast. So I'm sure the students want some clarity. Go ahead, please. Yeah, another professor. The bonus for the students. Next question. Okay.
In your calculation of a number of conducting channels, have you considered inelastic scattering due to electron Fermi?
Yes. So the question is, what about elastic scattering? So I took the most optimistic situation possible, which is that there is no elastic scattering and you're limited by the. If you put in elastic scattering, your clock speed is going to get even lower because you won't be able to deliver. But if we are able to go to carbon nanotube transistors, they are regarded as ballistic. That over these short distances will be. In fact, even in today's transistors, we're very close to scattering length. That enabled me, because I neglected elastic and inelastic scattering, I neglected it, I was able to reduce it. But if I would include the elastic scattering, it would just make matters. We have a fundamental upper limit based on. I want a question from the student. I see you prompting each other to ask the question. Go ahead. Okay, let me ask you, what do you think of that that undergraduate experiment from Cornell? They claim to have seen. Thoughts on that one? At room temperature, so it violated every rule people thought up till then. Room temperature would have been discovered just two vibrating wires. As the wires pull apart, this eventually go to infinite resistance. The last conductivity you have, where you go to zero conductivity, the last one. Cornell is very strong in solid state, so they put that. I don't know. I found it online. That picture I found online from the Cornell website with that class number. So it could be. I know you told me. It had both numbers. To impress you, I showed only the undergrad number, but undoubtedly, theorists who have to take the experimental lab that they hate at Cornell, undoubtedly they're forced to do this.
I just make a comment. A few years ago, Patrick Lee, the professor at MIT, who gave an IAS talk in similar case.
I was here when he gave his talk.
Yeah, he was trying to do it, and in the physics department, HKUST, we trying to hook up some student trying to do this exactly the same thing, trying to see what's the fundamental conductance that you can see over a very short time, which is a quantum phenomenon. Normally, you don't see it at room temperature. But what Patrick Lee was trying to make a case that all you need is short enough time that you can see it. You could see it.
Yes, that's right. And so I'm glad I'm not the only one telling you that. Okay, so we have a student with a question. Okay,
I
go.
would say that Cornell's pictures of the experiment, because I don't know how they figure out these 26 events.
You want me to show display the picture again? Let's see. Here's the picture. Okay, so they just have an ohmmeter. They're vibrating at a low frequency, which is the vibration frequency. While they're vibrating, Eventually, the wires pull apart and you go to zero conductivity. But before it has zero conductivity, it has this big plateau, 26 kilometers. The picture is, of course, artistic conception that you have a string of atoms. Of course, it's not really a string of atoms. It just, there's a final point that breaks, and finally the wires pull apart. At that point, there's only room for one quantum channel. So I would assume, I don't assume it's really a string of atoms like this. But when I first heard about this was when low temperature physicists were doing this. I said, wow, this is so good. We ought to do this at room temperature. Nothing that says it can't be done at room. Well, that's beneath my dignity. I'm a low temperature physicist. But indeed, it was very shortly after that. Here's a quantum effect. Room temperature could have been discovered in the 1890s. They had ohmmeters in the 1890s. They could have measured resistance. Now, a little bit about the speed. Maybe they didn't have oscilloscopes. Would have been a little difficult. But not an experiment that requires modern technology. It does not require low temperature. Thank you very much.